Good morning. This is Mr. Sandin. I'm going to show you how to work with right triangle trigonometry today. First thing you need to know about right triangle trigonometry is that you have to work with a right triangle. Sorry if I'm shaking the table here. All right, so I've got a right triangle, and you have to know which angle that you're going to start with and that you're going to pay attention and focus on. They usually use this kind of oval with the line through it called theta. Theta is just a Greek letter, and it's a variable for an angle. So if this angle is my theta, I could have chosen that one, but this one is the one I'm picking. The side opposite this angle is over here, and that's our opposite side. The side across or opposite the 90-degree angle is always the hypotenuse. And the side that connects the 90-degree angle and the angle you're working with is the adjacent side. It's also the side that's the leg that helps make up with the hypotenuse the angle you're working with. Now that could have been this angle, and we'll see that later today. So this is all in 12.1 right triangle trig. Page 645 is where it starts. Sine is the full word, but we abbreviate it S-I-N. We don't call it sin, it's sine. Sine of theta. Now, in this case, sine of theta, opposite over hypotenuse. So opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. Now what's really interesting is cotangent is adjacent over opposite. So you'll notice that these two are reciprocals of each other. It's also interesting to note that cosine is reciprocal with secant. So that would be hypotenuse over adjacent. And finally, cosecant is the reciprocal of sine, hypotenuse over opposite. So when you're going to set these up, that's what you're going to use, this setup. Now this is right in your book, so you can easily find it on page 645. There's also an example right there on 645 for you. Now I'm going to need to erase this so I can give you an example, so we have enough room to write the example out. All right, our example for this one is going to be a triangle where I've got sides 3 and 5. I'm not given the third side. Theta is here. So when we go to find this stuff, I first need to find my hypotenuse. So remember Pythagorean theorem, a squared plus b squared equals c squared. C is always the one across from the 90. So 3 squared plus 5 squared equals c squared, for example. So that's 9 plus 25 equals c squared. 34 equals c squared. And then we square root both sides to find c. Now, we can't simplify the square root of 34. It's just 2 times 17. So I'm going to leave it as square root 34. I'm going to get rid of that so that it makes it a little easier for us to do our continued work. I'll just erase this for now. All right. So the next thing I'm going to do is I'm going to find all 6 trig functions. Sine of theta. Now, sine of theta is going to be opposite, which is 5, over hypotenuse square root of 34. Unfortunately, we don't like to leave a square root in the denominator, so we're going to rationalize that denominator by multiplying top and bottom by the square root of 34. So this gives me 5 square root of 34 over the number. When I multiply these, they come out to the number 34. Next one I'm going to do is cosine of theta, which is adjacent over hypotenuse. So in this case, that's 3 over square root 34. But again, we have to rationalize this denominator. So I'm going to multiply top and bottom by square root 34. And I end up with 3 square root 34 over 34. Now, not all of them are going to require a lot of square roots here. Just a few will have square roots. So the next one I'm going to do is tangent of theta. Now that one's kind of nice. Opposite over adjacent, which is 5 over 3. Now earlier, we said that the tangent is just and the cotangent are reciprocals. So tangent, if I just flip that over, is going to give me cotangent of theta, which is just 3 over 5. Cotangent is adjacent over opposite. Cosine and secant are reciprocals. So therefore, I use this one, not that one. It's a lot easier to use this one. Square root 34 over 3. And finally, cosecant of theta ends up the reciprocal of sine, which is square root 34 over 5. So there you have the 6 trig functions for a particular right triangle. The next topic that we're going to hit is special right triangles. Now there are 2 special right triangles. There's the 30, 60, 90 and the 45, 45, 90. So if I'm working with a 30, 60, 90 triangle, these are degrees, then the way, that's not very good triangle, but the way this is set up, the side across from the 30 is the 1x side. So whatever x is, you just have one of those. The side across from the 90, the biggest side, is going to be the 2x side. And the side across from the 60 is the middle side, and that's going to be, this is weird, x square root of 3. Now, if we got rid of the x's and just had a side of 1 and a side of 2, we could have done Pythagorean theorem and come up with square root of 3 here, and these stay in proportion. So, for example, I've got 4 things to try with you. If this is my 30, 60, 90, and I start off with this side being 10, then I know that's the 1x spot. It's across from the 30, so this is twice as big, 20, and this one is going to be 10 square root of 3, because that's the x. The next one I'm going to try here. Here's our 30, 60, right? So the next one, this is going to be 15. Well, if that's 15, that's 2x. What's half of 15? 15 over 2, or 7.5, 7.5. So you could say 7.5 here, or 7.5, or 15 over 2. 7.5 square root of 3. Next example, what if I've got one where, here's my 60, where I get the square root of 3 side is 25 square root of 3. Well, that's the square root of 3 side. It's this one. So how many square root of 3's do I have? I have 25. So there's my x. My x is 25. So therefore, my 2x is going to be 50. Finally, there's always that curveball in there somewhere, right? Why? This is so easy. Eventually you come to something that's not super easy, but it's really not that difficult. What happens if this side is 18? Well, it's not got square root of 3. Hey, that's not fair, right? But if this is the square root of 3 side, 18 equals x square root of 3. I need to know what x is. So I'm just going to divide both sides by square root of 3. So x is 18 over square root of 3. Remember, we're going to rationalize, so I'm going to multiply top and bottom by square root of 3. That gives me 18 square root of 3 over the number 3. Well, 18 and 3 can reduce. This 18 can reduce with this 3. The 3 and the 18 reduce 1 and 6. So 6 square root of 3. So my answers here, x is 6 square root of 3. And twice that would be 12 square root of 3, because you're not doubling the 3, just the 6 out front. And that's how you do 30, 60, 90 special right triangles. The next type of special right triangle is a 45, 45, 90 triangle. And this has some special qualities to it as well. In a 45, 45, that's not a very good 45, 45, 90. It's a little too elongated. That's better. 45, 45, 90. And in a 45, 45, 90, this side is 1x, 1x, and x square root of 2. So, if those are our proportions, if our first one, for an example, has a side of 50, and that side of 50 is here, for example, then this side must also be 50. And then this side, x square root of 2 this time, 50 square root of 2. Now let's try that again with a different setup. Say the side over here is 8 square root of 2. Well, that would force, well, x square root of 2, 8 square root of 2, 8 is x, so those are both 8. Finally, what if we have a triangle, 45, 45, 90, and the side over here is 8. Well, 8 isn't got a square, doesn't, have a square root of 2, so 8 has to equal x square root of 2. I'm going to go ahead and divide both sides by square root of 2. So x equals 8 over square root of 2. Well, we can't leave it like that, so we rationalize. Square root of 2 times square root of 2 equals the number 2. And of course, the 8 and the 2 reduce. It doesn't always happen that way. If that were a 7, then it would be 7 square root of 2 over 2. But this reduces 1 and 4, so x is 4 square root of 2. So I can fill it in 4 square root of 2, 4 square root of 2, and I am done. Next topic that we're going to hit here is we're going to deal with, let's see, just finding values of something like cosine of, what was it, 63 degrees, for example. If I'm trying to find that, I need to take out my calculator, and now make sure it's in degrees, because there are radians and gradians. Make sure it's DEG up there. If you have to, you're going to have to look up how to change it on your calculator. If you have this kind of calculator, you just have to hit mode. See how it has it up here? Mode 4 in this case. It's already in degrees, so I don't have to do that. In this calculator, you type the degree first and then hit cosine, and it fills your display. So when you do that, let's see. That's what you get. Well, that's great, except we only want it to 4 decimal places. There's 4 decimal places. When I look at this one to round it, that makes this go up by 1. So it's 0.45. Now, because that went up by 1, that pushes this up 1. 40. So 39 becomes 40. And there's your value of cosine of 63 degrees. Now, what happens if you're given one that's not one on your calculator, like cotangent of 20 degrees? Well, it turns out we know that cotangent is 1 over tangent of the same degree, and that's 1 over, now I've got this long decimal, 0.36397 0234. Now, I only write that out because that's what's on the display. You should, most of you, have a button on your calculator that says 1 over x. And if you hit tangent of 20 and then hit 1 over x, it gives you the value of 1 over tangent of 20. And that comes out to approximately, let's see, 2.747